Hi there, my name is Elizabeth Alters, and I'll be presenting to you today the research that I did this summer on determining the total yield of alpha capture reaction products from measurements in a limited sample of charge states. And I did this research with my mentor, Dr. Hinnefeld at Indiana University South Bend, and my other mentor, Dr. Manuel Kuder at the University of Notre Dame. So St. George recoil separator at the University of Notre Dame is actually devoted to studying alpha capture reactions produced by a heavy beam using inverse kinematics. And this method, as opposed to the standard method or the light beam method, actually uses the heavy element as the projectile instead of the light beam, and it uses the lighter element, so helium in our case, as the target. And St. George then transports the recoiling reaction products into the detection system while rejecting the projectiles that didn't interact with the targets at all. In order to determine the total reaction yield from the most abundant charge states, the charge state or the charge state distribution of the reaction products emerging from the helium gas target must be determined as well. The program Atasha we used to calculate charge state distributions for 20 neon projectiles and then 24 magnesium products passing through that helium gas target. And those calculations were then combined to determine the expected distribution of charge states detected, charge states of the detected 24 magnesium reaction products. So St. George is a recoil mass separator used to study alpha-gamma reactions at Notre Dame's Nuclear Science Laboratory. So these reaction rates are measured in order to help us understand nucleosynthesis and then the energy produced that occurs during helium stellar burning, or stellar helium burning, I'm sorry. And St. George actually features 6 dipole magnets, 4 quadrupole magnets, and then 1 wine filter. And as you can see in that figure below, T1 is where the beam actually enters, and then it passes through until it gets to that wine filter. And as I said before, that wine filter filters out all those projectiles that didn't interact with those targets. And so these 6 dipole magnets only select one product charge state at one given time, and then it delivers those products to the detector station and counts them. Only the most abundant product charge states have a high enough production rate to actually be included and counted. So a product charge state could also have the same charge to mass ratio as a different charge state of the projectile. So in example, the 24 magnesium 6+ charge state products, and then the 20 neon 5+ charge state projectiles. And in that case, the products actually aren't detectable, and that's due to the projectiles being several orders of magnitude larger than the others. So the charge states in the 4+ and lower actually can't be detected as well because their magnetic rigidity is too large for the dipole magnets to bend the trajectories enough. And as you can see in that graph below, it just displays the 24 magnesium experimental yield that was measured versus those charge states. So the charge state calculations, the projectile charge state can actually change as it travels through that helium gas target, as well as while it passes through the rest of the target. So the charge state distribution of products emerging from that target depends on the evolution of the charge state of the projectile before the reaction and the product after the reaction as they pass through the gas target. We used Atasha, which is a standard software tool for calculating how charge state distributions change as ions pass through matter. And we used Atasha to do a spreadsheet calculation in order to combine the charge exchange before the reaction and the charge exchange after the reaction in order to predict the final product charge state under 2 assumptions. The first being that it picked up a bare 24 or a bare 4 helium nucleus, or it picked up a neutral 4 helium atom. And as you can see with these percentages there that are highlighted, as well as that bar graph, the neutral 4 helium pickup assumption matches the measured charge state distribution better than does the bare. So future directions that we want to go with this, we know that Natasha does an imperfect job calculating the evolution of charge state distributions for ions passing through helium gas. We can see there with those scatter plots that the measured charge state distribution with specific thicknesses hits equilibrium a lot faster than does the calculation from Natasha for the same thing. So as I said, it's still ongoing. We're hoping that we can identify a way to scale the Natasha output to match our measured data in the future. And we also want to answer a couple questions, or at least we hope to. We want to know specifically if Natasha can be adapted for gas targets since it was originally made for solid targets. And we also want to know, are the product charge state distributions measured so far with St. George consistent with equilibrium charge state distributions for those ions passing through helium? Also, my second mentor, Dr. Manuel Kuder, has reprogrammed our spreadsheet calculation into a C++ program, making it far easier to explore those possibilities in the future. And there is my works cited and my acknowledgments. Thank you so much for listening. Bye-bye.